Hello, team. Today's challenge is the circular prime challenge, where we take a number, rotate the digits inside of it, and determine if all those variants are prime. So, very interesting challenge and something that we can take on. In fact, we've seen both parts of this in various other challenges. So, for primes, we've seen things like unnatural prime, the nth prime challenge. We've even seen a variant of this in some of Divisors, if you've done that challenge. And then on the other side, for rotating items in an array or a list, we have message decoder and array shift and a Star Wars theme called Speak Wisely You Must, right? A bit of a fun one. And all those kind of revolve around this idea of shifting things within a string or an array. And we are going to combine some of each of those challenges into this one. Okay. The key here is that we are getting a number, and in order to make this easy for ourselves, we need a string. So right out of the gate, way up here, we can absolutely do that. Okay. We're just going to go const n string equals, use the equal sign, n2 string, just like this. Okay. Now we need a way to get our primes. And again, if you've done other challenges, you probably already have this function set up. So this won't be the first time that I use this exact function for this, because it's efficient and easy. Okay. So we're creating a new function called isPrime, just like this, and we're going to send in that number. Okay. So in this case, we've converted to a string. We're going back to a number. A little bit of inefficiency there, but the two will line up nicely in the end. You'll see, hopefully. Okay. If, okay, our first test is if num is less than or equal to 1, because if it's 0 or 1, well, we don't really need to do anything. And in fact, if it is, if it's less than 0, technically it's an error. Maybe we should have an error state, but for us, we can just return false, just returning early there. Okay. So 0 or 1, we aren't going to do anything with those. Let's get rid of those, and let's spell return correctly. Okay. The next step is our loop. Okay. So for let I equal 2. Okay. So we're starting at 2. We don't need to start at 1 because everything's divisible by 1. So save us a trip. Okay. But we do start at 2, and then I is less than equal to, less than equal to math dot sqrt square root of the number. Okay. And this is key. This is what makes the magic happen. If you think about a number like 36, the square root of 36 is 6. 6 times 6 is 36. Easy. Okay. But the way that we are working this is with the thinking that everything before that is tests everything that comes after that. Okay. So as an example, you take 2. Okay. 2 is the first one, and we're going to hit that right away with 18. 36 divided by 2 is 18. So in theory, we've already tested 18 because we've tested 2. Hopefully that makes sense, right? So we don't need to test 18. We've already done it. By testing 2, we've tested 18. By testing 3, we've tested 12. 4, we've tested 9. And of course, 6 is 6. If it's not a clean square root, we don't need to worry about that because it is less than equal to. So as soon as we go over that, we've stopped the loop and we're in a good spot. Okay. Right here, we are going to increment that. The nice thing about this too is that it keeps it really small, right? It keeps it really small. Like we're going to exit out of here in a second. So let's finish that and then we'll keep talking. Okay. That is whatever that number is, percent, which is modulo, right? Modulo I equals 0. So an exact equals, no inefficiencies there, right? In this case, we return false again. Okay. And then to finish it out, we return true. If we've hit this, it is in theory a prime. Okay. But if it's less than equal to 1, we return false. If it If it divides cleanly by any number inside of here, we also return false because it's not, okay? Now, here's the key, okay? I said return early, okay? And that's one of the nice things about this is that on the one hand, with that square root, we keep the loop really small. In the case of 36 again, we only do 6 loops if we were doing all of those 6 loops. In the case of 81, we would do 9 loops if we were doing all 9 loops, okay? And even for, say, 10,000, the square root of 10,000 being 100, we would do 100 loops if we were actually going to do all 100 loops. And what that means is that as soon as we find anything in here, we kick out of this function. So for, as an example, 10,000, it's divisible by 2, so we are only going to do that exact first loop, and we're done, right? The only way that this would happen is if we did all of the different things up to the square root of number, which means that in theory, it can be very small, right? If you're testing really big prime numbers, then maybe it takes longer, right? That's the nature of the loop, right? Where performance is a factor of how many times it has to go through. But for us, this gets the job done, and now we can use it, okay? So back to our circular prime here, okay? We have this. We actually need another loop, okay? So we are going to go let I equal 0 this time, okay? Because this is going to be a standard loop. I is less than nstr, capitalize it, just like this, dot length. That's the length of the string version of the number, okay? And of course, I++ to round it out, and we do stuff, okay? What do? Well, we need to cycle the numbers, okay? So that's the first part. Let's do that. We probably could have used a const here because we're inside of the loop, but I'm going to leave it as a let, and we're going to set that equal to a new string, which has this and this. What are these 2 pieces? Well, it's the string, but we're going to slice pieces off of it, okay? So nstr.slice, and we are going to go from I to the end. Whatever I to the end is, we're just going to get it, okay? And then over here, we're going to do the exact same thing. So nstr, do a right, dot slice, and this one is going to be from 0 to, but not including, I. And this kind of saves us on that first loop, actually. So slice 0, right? It's going to go from 0 to the end, which is the entire string, whatever that is. And then for this part, it's not going to return anything because it goes from 0 to 0. Well, it doesn't capture that 0, so it's not returning anything, right? Which means that it returns nice and clean, gives us a nice string to work with, and we can test for prime, okay? So right down here, if not is prime, okay, just like this, we're going to test against whatever the current is. But remember, current is a string, and we want a number. So let's go and make sure that that's a number. We're going to coerce it with the plus sign, okay? And if that's all good, then we return false. Otherwise, we return true. And that should do it, okay? So a couple things here. You will probably see me use this in other videos whenever we have to deal with primes. It is very efficient. There are other versions around. I will link to a Stack Overflow article that has a different version, which is less lines. I like this. It's nice and clean, right? I don't need to fuss around with it. So we do this. And then down here, we do another loop because we have to spin the string version of that number. And then we pass it in, we test it, and we return as soon as we get one that is not prime, right? If all of the different things are prime, we're good. We can kick it out the door and make it happen. Otherwise, we return as soon as we find something that fails. And we do that for both those functions. As soon as we find something that doesn't meet our criteria, we return early and end it, okay? So, very efficient. Could we have done a few things different, like use a plus sign instead of this string, instead of this template literal? Yeah, maybe, right? And I'm sure that there are other versions too. Please drop them in the comments, right? I'd love to see them. Today, this is my version, not every version, obviously. But yeah, comment. Let me know how you figured it out. And I will see you in the next one.